Okay, so next exam is a week from today. It covers everything we've done since spring break, so starting with Dr. Thompson. And also it's mostly this sequences and series stuff, and then what Dr. Thompson did. What we do next week will be on the exam. Monday and Wednesday will be on the exam. Okay, so we're gathering all these what I call tools for a toolbox for analyzing series. So remember that the bottom line here is a sequence is the list, and then the series is where you take all the numbers in the list and you add them up. And we know we have some abbreviated symbols for that, right? So, but we're not scared by those anymore because we know this, right? We know that we're just talking about a list, and then we're adding up all those terms in the list, right? We always keep that in mind. So here's in terms of analyzing series for whether they converge or diverge, right? The divergence test, the geometric series, p-series, comparison test, and alternating series test. So this is the accumulation of tools that we have so far in our toolbox, and the web work that you do for Monday, you won't know what applies. So there's the skill you have to have of coming to a series and figuring out what applies. What do we always do first? Looking at a series. We look at that sequence and we say, what has to be true about that sequence? That sequence has a limit of 0, right? It has to converge to 0. If it doesn't, you're done. Series does not converge, right? That's the only chance that a series has to converge is if the list approaches 0, right? That's the only chance. Those are the ones we're interested in, right? Those are the ones that we use the rest of the tools for. So do you know these, right? So there's definitely a memorization aspect to this. Can you write the headline for each one of these tests, right? Can you write the headline? You get 1 minute to talk to the person next to you. What's the
So, like, if we know a series that's like larger than the one argument that converges, we know ours converges.
Okay, so let's do the headlines here. So if you didn't get through them, that's okay. We just need the time for the new stuff. But divergence test, again, if that limit doesn't go to 0, the series diverges. Boom, game over, right? Geometric series looks like that. A r to the I minus 1. Convergent when the r, the multiplier, right? What's r? It's the multiplier that gets us the next term, right? We keep multiplying by r over and over again to generate terms. Okay? If that r is a fraction, we're going to keep taking a fraction of what we had before, and it will go to 0, right? And then the sum is a over 1 minus r when it converges, right? Okay, p-series, 1 over I to the p. Divergent, 0 less than or equal to p less than or equal to 1. Convergent for p greater than 1. Comparison test. The series is divergent if it's bigger than a known divergent series, or if all the terms are bigger than a known divergent series, or it's convergent if it's smaller, all the terms are smaller than a known convergent series, right? And then there's the two cases where it's like unknown, right? If you got something smaller than a divergent series, who knows, right? Or if it's bigger than a convergent series, who knows, right? Alternating series test we did last time. If the positive version of all the terms decreases to 0, then also that's all we need then. All we need is the positive terms decreasing to 0, and then the alternating effect will make the sum convergent, right? We'll make the sum convergent. Okay, ratio test is what we're going to do today. All right, so you got to have these memorized. And then you have to be able to identify, just come to any series and identify which one applies and apply it correctly. And that's what your homework for Monday night is they're just all thrown at you, okay? They're just in any order. Oh, notice on that homework, like the whole first set of questions, one attempt. One attempt, because it's just like all it's saying is asking conversion or divergence. So you have to, and with these homework problems, you can get them right, but then overlook all the value in the problem, right? So you have to train yourself, take the initiative yourself to get what that problem is trying to teach you, rather than just getting it right, getting the credit, and moving on. Okay? So they're all excellent questions, but it depends how you approach them. If you're really getting out of it what you should. Okay, so take your time to analyze them instead of just having a mindset of getting the points and moving on. Okay, so let's just review this. What was absolute convergence? Absolute convergence was when a series, whether or not it has the alternating help, it will converge. That's what we said, right? If the series converges, whether or not some of the terms are negative, it's called absolutely convergent. And what's it called if it needs the alternating effect to help it converge? That was conditionally convergent. So if you take away the alternating effect and it diverges, and it was convergent before, that's conditionally convergent. All right, so that's what we said, right? So absolutely convergent, if you take the absolute value of all the terms and it still converges, it's called absolutely convergent. If you take the absolute, so you got a convergent alternating series and you take the absolute value of them and it doesn't converge anymore, conditionally convergent, right? It's conditioned. The condition is that it alternates, right, in order to converge. All right, so we worked through these last time. So this is somewhat of a test for absolute convergence. This is one way to test for absolute convergence. Look at the series with all positive terms and analyze that if you can. All right, so that's kind of using the definition of absolute convergence to analyze it. But then there's another, we're not going to do this. There's another test for absolute convergence called the ratio test. The ratio test, okay? So we can apply the definition, just make all the terms positive and then analyze that series, or we can use what's called the ratio test. So what the ratio test says is you got this series, you're going to make a new sequence, and that new sequence is going to be this. You're going to take the ratio of the next term to the current term. Take the ratio of the next term to the current term and make a sequence out of that. So you look at the second and first term. Second term over first term. That's the first term of the sequence. Third term divided by the second term. That's the next term of the sequence. Fourth term divided by the third term, etc. Make a sequence like this and look at the limit of that. If that limit is less than 1, then your series is absolutely convergent. If that limit is greater than 1, divergent. If the limit equals 1, the test yields no conclusion, and you gotta use something else. You gotta use something else. Okay. So what I circled in blue, you're making a new sequence, and you're not gonna list out the terms like I kind of said, but instead you're gonna find the formula for the general term. You're gonna find the formula for the general term, and you're gonna analyze that sequence using all the stuff we did at the beginning of this unit, which was analyzing sequences, right? Analyzing sequences. So let's see what this ratio test is about. It's really about a geometric series. So in a geometric series, how do we generate terms? How does each term get generated? That's the right idea, but watch out for the word add here. Yeah, right. Yeah, you were thinking the right thing, but don't say add because, yeah, so every time to get the next term we multiply by r, right? And when does this converge? Okay, so now here's any series, right? Any series, you could write this way: a1 plus a2 plus a3 plus a4, right? Plus a5, etc. plus an minus 1. Okay, so let's think about, if all we knew was those, let's think about what would you multiply a1 by to get a2? What would you multiply a1 by? And you don't know anything about these. You don't know anything about what a1 or a2 is. But how could you form an expression that if you multiplied it by a1, you'd get a2? What would it be? a2, what? Divided by a1. Isn't it true that if you multiply a1 by a2 divided by a1, you get a2, right? Same thing. What would you multiply a3 by to get a4? The ratio of a4 divided by a3. This is just arithmetic, right? This is just arithmetic. Algebra. So what do you multiply an by to get an plus 1? So now the general term would be an plus 1 over an. So in a geometric series, the multiplier is r, and it stays constant. In any series, what's the multiplier in any series? An plus 1 over an, right? So what is the ratio test saying? It's saying, look at this sequence and take this out. Take this out to the million, billion, trillionth term, and look at this ratio. This ratio is the multiplier to get to the next term, just like r is the multiplier to get the next term in a geometric series. So if that converges to something less than 1, what's going on? It's kind of like this sequence, this series is becoming like what? Geometric, right? So if this say this multiplier converges to 1/2, then in the long run, this is really just a geometric series with an r of 1/2. Make sense? So this ratio represents like a changing value of r, right? As you go from term to term, it's like your multiplier is changing. But if in the long run it converges on a number, then it's like this thing is converging on a geometric series in the end. And so if that converges to a multiplier that falls in our range for convergent geometric series, then it will converge too. Does that make sense? So the ratio test is just about seeing if the series is turning into a geometric series in the end. Make sense? By looking at what the generic multiplier would be. And does its limit exist does its limit land between -1 and 1? Pretty cool, huh? All right, I think so. So let's see some examples. First example is this. So what do we need to do? We need to write the formula for this sequence right here. For this sequence right here, an plus 1 over an. Or in other words, the sequence of multipliers from one term to the next in this series. Right? Okay, so what do I have? ai plus 1, right? Those aren't n's, those are i's. All right, so ai plus 1. So ai plus 1 is going to be -3 to the, sure, we can use j, whatever, it doesn't matter. So we got j here. So j plus 1 divided by that's a to the j plus 1. Right? So all the j's just are j's plus 1s, and we're divided by what? A sub j. A sub j, which is just that. So we're going to look at this sequence. Now that we're going to make this formula a lot simpler, right? So that's looking pretty ugly, a fraction over a fraction. So we do algebra to make that simpler. And then after we do the algebra to make it simpler, then we're going to take the limit, right? We're going to apply our, should be I. So this should agree. All right. So oftentimes you're going to be setting up this fraction of fractions, and we can actually skip this step, and we can start with, from here on out, so it's good we do it the first time, from here on out we can do it as the product of what, a sub I plus 1 times the reciprocal of a sub I. And that's this next step I'm going to do. I'm going to invert and multiply, right? I'm going to take this down here, flip it and move it up and multiply. And this is the step you can start with on this test, okay? So you don't have to write this ugly fraction to start. So in the future, on future problems, you can just start with this. -3 to the j plus 1, j plus 1 cubed times, what will it be? J cubed over -3 to the j. All right, so from here on out, you can just start with that step. So instead of writing this big ugly fraction, you can write a sub I plus 1 times the reciprocal of ai, and that's what I did there. So we can start there. All right, so we'll simplify it here. And when you do that, you're looking for things that are alike. So look, -3 to the j plus 1, -3 to the j. If we think about the meaning of that, what does that mean? a bunch of negative 3's multiplied together. Here's also a bunch of negative 3's multiplied together. And so when we simplify that, what are we left with? There's one more negative 3 in the numerator, right? So we keep on negative 3. And then we have times j cubed over j plus 1 cubed. And we think back to our, so we've got this sequence, this formula for the sequence. And now what are we doing? We're looking at the limit as j gets big of the absolute value of negative 3 yeah. Yep. It's absolute value. Okay. And so we remember back to our sequences. We're experts at sequences. We got j cubed over j plus 1 cubed, and we're going to let j get really big. And then so that limit of that thing is a sequence now. Sequence. Did you forget all that we did about sequences? So this j cubed, what's the leading term down here? Another j cubed, right? So this is like a rational function. J cubed over j cubed, 1. Right? So the limit of this thing is 1. So and negative 3 doesn't care what j does. J can do whatever it wants. It stays negative 3, right? And so what is this limit? Positive 3. So in essence, what does this tell us? What does this tell us? This tells us that in essence, what is this series doing? I'm not talking about convergence or divergence. What do we talk about? So the fact that we got a 3 here means this series is doing what? No, not quite. It's turning into what? A geometric series with r equals 3, or actually negative 3, okay? But so, yes, it's like turning into a geometric series where your multiplier is actually going to flip between negative 3 and 3. It's because it's alternating also, okay? And we know that a geometric series that, in the end, in the long run, multiplies by 3, then multiplies by negative 3, multiplies by 3, multiplies by negative 3. Is this going to converge? Never in a million years, right? It's just going to blow up. And so that's why if this thing is greater than 1, it's just you're thinking about it as a geometric series. So this thing's divergent. Questions on that example? Okay, let's do one more and then I'll give you some. Oh yeah, question, sorry. It's well, r. So a real geometric series has a constant r. Every term is multiplied by that same r. The ratio test is testing to see if the series is like kind of evolving into a geometric series in the end, because that multiplier is going to change. But does it change in such a way that the limit ends up being like getting really, really close to 1r? So yeah, it's like is the series evolving into a geometric sequence? Okay. Next question. And then you can evaluate it like a geometric series. Yeah, so that's why this is exactly the same thing as geometric, right? If that L is less than 1, since we took the absolute value of it, it's less than 1. That's the same thing as R being less than 1, convergent, right? If R is greater than 1, divergent. Right. Yeah. No. So lots of the basic ones, you're going to get L equal, if you're doing like a lot of the ones we've done so far, you'll get L equals 1 a lot. Yeah, so it's not like this one will be able to do them all.
Would it be incorrect to multiply out the j plus I to the third?
No, I mean it's just so I kind of talk through that. Yeah, when you multiply through, then your leading term is j cubed, and then that's all you need for the limit. So it's not incorrect. Yeah, so it's j cubed, what, plus 3j squared, plus 3j plus 1. Okay. But now to evaluate that limit, all we need was this, right? We look at the leading terms. If they have the same power, then it's just does that make sense? Right. Yeah, so if you need to multiply that out, perfectly fine. Yeah.
Why can't we just compare the top half of the fraction to the bottom half of the fraction?
Yeah, so there on this one, yes. Yeah, if you want to do some more reasoning, it's possible to solve some of these without the ratio test. Yeah, and that's great if you want to go for that. But you know, this subject is kind of a combination of like showing mathematical proof of things and also reasoning. So we don't want to fall too far on one side or the other. Other questions? Okay, next one. Can I erase? Here we go. So let's see if you can write out the first step, and you can write it out as a product, right? So it's going to be a sub I plus 1 times the reciprocal of ai. See if you can get that step right. See if you can get that step right. Okay, check and see if you wrote the same thing. Yeah.
Can we just ignore the -1 to the I and I plus 1 because we're taking absolute value?
Yeah, but only because it's -1. Like the last one, we couldn't because that 3 was important, right?
Yeah.
Yeah,
So
right. Yeah.
not any plus.
Yeah, that's right. Because then you're always going to get one -1, and you're going to take the absolute value of it, and it'll go away. That's right. Okay, so let's just. So she brought up a really good point. Whenever you have -1 to the I, what are you always going to end up with? You're just going to end up with one more -1 in the top, right? And so because we're going to eventually take the absolute value, it's kind of inconsequential. Now the -3 we got last time was very important, right? So if it's something other than -1, you don't want to. That's going to be important because it's going to change the value of the ratio. But this will not, because you'll just get a -1. Absolute value is 1, so it won't. So that's, you can watch out for that. Okay, so now we kind of, to analyze this, now we're going to take the limit of the sequence of the absolute value, and we want to kind of combine like things here. So it's 7i plus 1 squared over 7i squared. And then I cubed plus 4 over I plus 1 cubed plus 4. Limit there. Limit of that part of it as I gets big. 7i squared in the top, 7i squared in the bottom. Limit of this as it gets big. Leading term, I cubed. Leading term down here, I cubed. Limit. Overall limit. What can we say? Nothing, right? So what is this saying? It's kind of like saying this series isn't becoming geometric, okay? It's not becoming geometric with some, it's not evolving into some geometric series with an R value. So we got to go back and use other methods to do this. So we look at this. What kind of series is it? So no conclusion, right? Ratio test doesn't help. Ratio test doesn't help. But actually, if we look at this, and but it was good to practice the algebra, practice the arithmetic. But if we had looked at this without the ratio test, we could have done it after last time's class. What kind of series is this? This is alternating series. So what about the alternating series test? What about the alternating series test? What was that? The alternating series test was look at the positive version of the terms and ask what question? Are they decreasing to 0? Remember that? So are they decreasing to 0? So 7i squared over I cubed plus 4. Does that sequence, that positive sequence, do those terms decrease to 0? Yep, you got I cubed, you have a greater power in the denominator than the numerator. So since this decreases to 0 and it's alternating, conclusion? Converges. Okay, it converges. Now the question is it absolutely convergent or conditionally convergent? So by the alternating series, let's write this out. By alternating series test, the sum converges. Since BI decreases to 0. Now, conditionally, so we want to see, does it absolutely converge or conditionally converge? The ratio test didn't help us. So all we have left is just the definition of absolute convergence. What was our definition of absolute convergence? Just what do? We're going to look at just take off the alternating effect and analyze that. So if you take off the alternating effect and analyze the remaining series, if it converges, then this thing is absolutely convergent. If it diverges, then we have conditional convergence. It needed that alternating to do it. So now just look at 7i squared over I cubed plus 4. Okay, I have a vote for converges in front. Another vote in the back for converges. Why? Because that goes to 0? Doesn't guarantee that it converges, right? If you have a sequence that goes to 0, it doesn't converge that the series converges unless you have the alternating effect. Well, now we're taking the alternating effect off. And that's, right, jury's out, right? Yes, that does go to 0, but that's not enough, right? So we think about, what did we talk about last time? Could we use comparison? No, because the denominator's bigger and the numerator's bigger than what, like I squared over I cubed. So if we were thinking about I squared over I cubed, we're taking 7 times, that's bigger, and also adding 4 makes both the numerator and denominator bigger, so we can't do direct comparison. But we can do that kind of indirect comparison thing where we look in the long run, what does this thing become in the long run? In the long run, it becomes like 7 over I. You see that? If you just look at the leading terms, that sequence kind of turns into 7 over I in the long run. And so we ask, does that converge? Would that series converge? If that series converges, then this one will too, because this one is kind of evolving into that. Does 7 over I converge? Yes or no? No, this is 7 times the harmonic series. This is 7 times the harmonic series, which diverges. So, is this thing conditionally convergent or absolutely convergent? Conditionally converges. Since, I don't have room to write, but we'd write what? What could we write? We write, since the series 7i squared over I cubed plus 4 in the long run is like the series 7 over I, which is essentially the divergent harmonic series. And that's what you would write. You'd write all that stuff. Since 7i squared over I cubed plus 4 evolves into 7 over I, and that series diverges, then our series diverges. And so it needs the alternating help to converge. It needs the alternating help to converge, therefore it conditionally converges. Okay. Questions on this one, right? So we use a lot of stuff that we've talked about. Sequences, the ratio test, the alternating series test, absolute convergence, harmonic series, right? So that's sometimes these problems involve lots of the tools we've acquired so far. Any question? Okay, your turn. Can I erase? All right. Okay. So there's a sub k plus 1. What's 1 over a sub k? Let's see here. Thomas. Okay? And so if we have negative 1, we just have one more negative 1 in the top than the bottom. We're going to take the absolute value eventually. Also, let's do that. So we're going to take the limit as k gets big of negative 1. And then 2 to the k plus 1 over 2 to the k. And a factorial over all right, 2 to the k plus 1 over 2 to the k. Let's see. Emma. What's that? 2, right? There's one more 2 in the top than the bottom. So this whole thing is equal to 2. It's not even the limit. It's just equal to 2, right? Okay? Here. And then this is equal to, so we're not even taking the limit yet. So this k factorial over k plus 1 factorial. What do we think? Hayden.
1 over k plus 1.
Right, because what is k plus 1 factorial? It's k plus 1 times k factorial, right? It's k plus 1 times k minus 1 times k minus 2. So k plus 1 factorial is just k plus 1 times k factorial. So the k factorials go away. So we have the limit of, what, 2, so that this goes away. And we have the limit of 2 over k plus 1. Equals? 0. Conclusion? Absolutely converges. What is this saying? So not only is it becoming geometric, but it's becoming geometric such that what? The multiplier is becoming 0. Right? You can't do any better than this, right? You can't do any better than this. Not only is the sequence going to 0, but the number that you end up multiplying by each time is getting infinitely small. So that's very powerfully converges, right? Very powerfully converges. Because it's like, in a geometric series, it's like you multiply by 1/2 every time, and we know that that converges. Well, imagine if that 1/2 kept getting smaller, and it went to 0. That's what we've got here. All right, next one. Any questions? Okay. Go. Okay, look at my first step. See what you think. Chase. Okay, so he's asking about this. Is this right? So what would I change this to make it right? 3 times quantity k plus 1. So k itself, we add 1 to k itself. So 3k plus 1 does not add 1 to k. So, but at 3 times the quantity k plus 1 does. And so then it becomes what? 5 to the 3k plus 3 plus 3, not plus 1. Do you see it? Okay. Ingrid, what is k plus 2 factorial over k plus 1 factorial? What does that equal? Just k plus 1? 1 over k plus 1? Meet, what do you think? What's k plus 2 factorial over k plus 1 factorial? K plus 2. What do you think? Yeah, because k plus 2 factorial is k plus 2 times k plus 1, then down. So it's really k plus 2 times k plus 1 factorial. So the k plus 1 factorials go away. So that whole thing's k plus 2. And what is this? Here we have 3k number of 5s multiplied together. And then we have more or less 5s multiplied on the bottom. How many more 5s do we have? There's 3 more 5s in the list here multiplied, or factors of 5, than there are here. Therefore, times 1 over 5 cubed. And then we're going to take the limit as k gets large. So the limit as k gets big of k plus 2 times 1 over 5 cubed. What's the limit of that? That gets big, right? So k plus 2, this is just going to be 1 over 125, doesn't matter, but k plus 2 is going to get big. And that's certainly greater than 1. So not only does the sequence itself diverge, but it diverges in such a way that the multiplier just keeps growing, right? So this diverges very, very badly. Okay, just write this one down for practice. We don't have time to do it. But if you can